In this video, we are going to introduce our carboxylic acid derivatives. We're going to define what the heck is a carboxylic acid derivative, distinguish why aldehydes and ketones are not carboxylic acid derivatives, and then start to create parameters for reactivity and how we think about compartmentalizing our carboxylic acid derivative functional groups. All right, so first thing to know is that a carboxylic acid derivative is an acyl functional group that can be turned into a carboxylic acid via hydrolysis, that is to say, reacting with water under the appropriate conditions, causes that carbonyl compound to become a carboxylic acid. We use water as a nucleophile. We have an acyl substitution reaction across this hydrolytic breakpoint, and we generate a carboxylic acid. Your carboxylic acid derivatives are the acid chloride, the acid anhydride, thioester, ester, amide, and the nitrile. Don't forget about the nitrile. The nitrile is the black sheep of the family. There is no C double bond O in that compound, but nevertheless, it is a carboxylic acid derivative. Under the appropriate hydrolysis conditions, we can turn the carbon of that nitrile into the carbonyl carbon of a carboxylic acid. Now, if you ever hear me say hydrolytic breakpoint, I'm talking about cutting between the carbonyl carbon and the adjacent lone pair atom. That's essentially the visual slice point as we react our carboxylic acid derivatives. You might also hear me say slice and dice. Okay, we essentially react across that slice point, inserting our nucleophile. Now, aldehydes and ketones we talked about separately. Yes, they have a carbonyl, but no, they are not carboxylic acid derivatives because they do not undergo hydrolysis to form a carboxylic acid. When I react with water and acid, no carboxylic acid is generated. Instead, we have a hydration. Okay, there is a hydration, not a hydrolysis. And remember that hydrate is generated, and then there's this back and forth equilibrium. We form the hydrate, regenerate the carbonyl. We form the hydrate, we regenerate the carbonyl. Attached to the carbonyl carbon of your aldehyde/ketone, there is no inherent leaving group, and they characteristically underwent acyl addition mechanisms, whereas our carboxylic acid derivatives will undergo a characteristic mechanism of acyl substitution. Okay. Now, while we can't hydrolyze an aldehyde or ketone to a carboxylic acid, we certainly could take an aldehyde specifically and turn that into a carboxylic acid. But that would occur through a process of oxidation. We can transform an aldehyde into a carboxylic acid using our strong oxidizing agent, chromic acid. All right. Now, when we think about our carboxylic acid derivatives, we have three excellent electrophiles, which I call our more reactive derivatives. That would include the acid chloride, acid anhydride, and thioester. We then have four less reactive carboxylic acid derivatives. They're more poorly electrophilic. That includes the ester, the amide, the nitrile, and of course the carboxylic acid itself. When we react our more reactive derivatives, we could do so under neutral conditions, acidic conditions, or under basic conditions. Given their high reactivity, any of those conditions would be satisfactory to effect a downhill energetic transformation. For example, I can take the acid chloride and turn that into the carboxylic acid by just using water. Hella reactive. But if I were to try to just take water, okay, if I attempted to just use water transforming an ester to a carboxylic acid, I'm probably going to age a few years in the process there because that reaction would be incredibly slow and very ineffective. It takes an incredibly long amount of time for that to occur. So, for your purposes, think the less reactive derivatives, they need more vigorous conditions. More vigorous hydrolysis conditions would be reacting with water, acid, and heat. There we could see an effective hydrolysis to the carboxylic acid. Now, vigorous conditions at time might also mean reacting with base or simply reacting with high heat. Okay. So excellent electrophiles, your three most reactive derivatives, can react under neutral, acidic, or basic conditions. Neutral conditions usually suffice. And doing acidic or basic conditions would be essentially more vigorous conditions. Now, let me show you how that can ultimately be applied to thinking about the reagents required for a transformation. Let's say we come down to our reaction summary page here. Let's say in a hypothetical, you were asked to provide the reagents required for this transformation up top here. Okay, you were asked to supply reagents to go from the acid chloride to the acid anhydride. You would imagine looking at that acyl substitution slice point. You would then pull out that component visually, and you would then imagine it in its neutral form and its anion form. Then you'd ask yourself, well, does it matter if I react neutrally or under basic conditions? Does it matter? And the answer is going to be dependent upon the reactivity of your derivative. Well, because the acid chloride is a king of reactivity, it could react well under basic conditions or neutrally. Either of those two would suffice. Two versions that I imagined. But let's instead say that we go down to the carboxylic acid functional group, and we imagine a scenario where we're asked to provide reagents for this transformation here that I'm whiting out. Going from carboxylic acid to my ester, what I might do to imagine the reagents is look at the acyl substitution slice point. I'm going to pull out that structural component visually. I'll imagine the anion version, and I'll imagine that neutrally. Now, if I consider reacting the anion version with the carboxylic acid, I'm not going to get the ester directly because in this case, we have an acidic hydrogen that we remove just deprotonating to form a carboxylate ion. So that's not going to work here because of that acid-base reaction. And then if I just imagine reacting with an alcohol alone, because that's a less reactive derivative, that's not going to work. It's not going to be effective. But what would be effective is reacting with my alcohol, acid, and high heating. Okay, I use more vigorous conditions because it's less reactive. Neutral alcohol alone will not suffice. I need to use more vigorous conditions. So that's essentially to exemplify what we're saying here with the parameters. We have our more reactive derivatives and our less reactive derivatives, and that can help us think through the reagents required for a transformation. All right. The quick recap of this video is carboxylic acid derivatives are the functional groups that can be hydrolyzed directly to a carboxylic acid. That includes the amide, nitrile ester, acid chloride, acid anhydride, and thioester. Aldehydes and ketones are not carboxylic acid derivatives because when reacted with water, they do not generate a carboxylic acid. They only undergo hydration. But we do have access to go from aldehyde to carboxylic acid using our strong oxidizing agent chromic acid. And as you begin to think about your derivatives, I want you to organize those into your more reactive derivatives and your less reactive derivatives.